Hi everyone, so my name is Patrick Fougeray. I'm a CATIA technical specialist for civil engineering, and I will talk to you today about the hydropower digital twin that we can perform with CATIA and 3D experience. So I have a couple of slides first to introduce the topic. So first about our customers. So we are working on different geos for different customers using CATIA and 3D experience for dam and civil projects, so such as Hydro-Québec, SNC-Lavalin, WSP, Hatch, AECOM in North America. And also we have a lot of customers in China using our solution, like Yellow River Engineering Consulting, Chengdu Engineering Corporation Limited, and Shenyang Survey Planning, Design and Research. Just to give you some ideas about the people that are using our solutions. So what do we do for hydropower? So we have here the solution framework. So we cover, so first we have a common data environment, meaning that all the data is saved in a single source of truth. And from there, so we can access this data through a lot of different applications. So, and with those applications, we cover the full, the different steps of an hydropower project, starting with the planning, with CATIA, pre-feasibility studies, feasibility, the bidding, the design, the construction, and up to maintenance and operations. So we access the data through different applications, as I said before, and those applications can be from CATIA for design and engineering, but also we can have other brands that will access the data for, such as Geovia, for example, to build the geology model and to be able to design in context of the geology, or the simulation where we will simulate, so either simulate with finite element analysis or simulate the construction, for example, of the dam. So what are the values of CATIA for civil infrastructures? So first, we have a multi-scale approach. So we have we can work in multi-range. So from the micrometer for semiconductors, for example, up to 10,000 kilometers if you build, a big highway, for example, in CATIA. We can manage a large data, so we are really efficient in managing a lot of data for the project. So as you will see in the future, so we have a dam project sample where we have details. So we have all the earthwork, all the data, and we can go up to the bolts and all the fixation, for example, that will be used in the project. We have also high design accuracy, so we can work in a low LOD, low level of detail, or we can go also to LOD 400 plus with a lot of details in your assemblies and your parts. So we have also a multidiscipline approach. So we have a lot of specialized applications. So I was mentioning that we access the data from the common data environment. And from there, we have all the disciplines required for the design, for example, of a dam. So we have a steel structure, we can do steel structure, terrain and earthwork, MEP, road, bridges, tunnels, dams, and so on. And everything is in a common data environment. So to manage the complexity of the project, we have also tools for system engineering that I will show you a little later. And the idea is really to build the digital twin of the project, so here of the dam, to be able then to perform simulation, to experience actually the design. So we build the digital twin, starting with the feasibility studies, up to the maintenance and operation, and we can do in between all the simulation for the project. So what is also really important is that we do concurrent engineering. It means that all the users, all the designers, they see what the others are doing. So if you're like a piping designer, for example, you will see the steel structure in the project, and you will be able, through relational design, to attach your pipe to the structure. Meaning that if at some point the structure is moving, your pipe will follow, the fixation of the pipe will follow the steel structure, and you will have to update your design, but you won't have to redo. So the idea of concurrent engineering is to avoid to gather data coming from a lot of different softwares and to manage a lot of issues like clashes between the different tools, and to work in the context of the dam itself. And finally, in CATIA, so we have a lot of automations. So first, we have some automation that we call component-based design that allow you to move from a low LOD design to a high LOD design. And we can also build, so or the customers, the users, they can build their own templates, custom templates that they will be able to reuse to accelerate the design of their projects. And then we have ways actually to automate the deliverables, such as the drafting sheets, for example, or the bill of materials. So here a short introduction of the capabilities of CATIA. So we can import large point cloud with actually no limit in size. We stream actually the data, and then we can extract the terrain that we will use to perform analysis, such here as a watersheds analysis. You can also, here there are some topography analysis tools with the water drop path, for example, to visualize where the water will go. From there, you can isolate a catchment area. Of course, we can do like contour maps, for example. We can map orthophotos on the terrain itself to have a more context, so geolocalized images, for example. I was talking about templates, so you can create your own custom template for a dam, for example, that you will instantiate in the context of your terrain and the dam axis that was drawn here. You can adjust parameters like the height of the dam, the width of the dam, the water level, and so on. And then you instantiate the templates that will be automatically built in context with already available quantities. So we already have here the volume of concrete and the volume of water behind the dam. So through Geovia, we can generate the different geological layers in the area based on boreholes. And we can then use that to build the dam in the context of the geology, taking into account faults, for example, or other issues that will appear here. So then we can perform excavations, so in the terrain, on the ground, or on the rock here, for example. We have the capability to design the building itself for the powerhouse. So with windows, doors, through the catalogs that are delivered with the solution. So then we can perform, the steel structure inside, and we leverage actually the high capability of the surfacing tools that we have in CATIA for aerospace, for example, to build the turbine enclosure. We have tools to perform alignments. So, for example, here a tunnel alignment, horizontal alignment, vertical alignment, where we can see actually the geological layers in context also to see which geological layers we are going through. And from those alignments, we generate a 3D alignments that will be used actually to instantiate, the tunnel, for example, or the road with the different layers. So everything in CATIA updates, meaning that if at some point you decide to change, for example, the profile of the road, the 3D will automatically update with the earthwork and so on. So we have also capabilities to do the rebars inside the concrete. So to do the reinforced concrete with dedicated capabilities for that. We can generate the steel structure based on a grid, adjusting the position. So we have here accelerators to instantiate faster the columns or the beams, for example. We can add trusses, and we can generate automatically the cut list with the weight of the different components. Then we have capabilities to generate 2D views. So here, we have some automation also, as I was mentioning. So we can either do, manually creating the design, or we can use some smart annotations. So for example, here it's a smart annotation that will automatically put the elevation of the different stage of the process. We can do rebar drawings, alignment drawings with the horizontal view or the vertical view. Here it's a bridge, or the vertical alignment views, and so on. So it was a short introduction. Now I will jump into some more live demo. So showing first one of the big value that we have in the platform is that we have access to everyone can access the platform. Here I'm in a web browser, and I'm able actually to visualize the data of the project, for example. So if I have, of course, if I am authorized to do that, and we can actually do that from any devices. So meaning here I'm on my laptop on the web, but I can also, if you can see here on my phone, I can also access to the same type of data directly from my phone. It's a web page, and I will be able actually to be able to visualize the project. So it has a lot of value. So here, for example, you will see the project, so that I can use to rotate and move. So the value here is really that it's not only the designers that will be able to access to the twin, to the digital twin. Everybody that is authorized to will be able to access the project and to perform some basic actions. So here, for example, I can see the work breakdown structure of the project. I can, hide or show some data. For example, I can access, the information on the different objects that are here. Such as, for example, the IFC attributes. So if I want to see the dam base quantities, for example, I can see the height, the length, the width, and everything that has been populated by the designers. So it's directly accessible through the web. I can visualize, 2D drawings also, in the web. I can so navigate here, for example, in the project, so the dam project. And I can do some basic operations such as measurements, for example. So to display, the volume of the dam. Or I can, if I move, for example, closer to the powerhouse here, I can also do measurements on the powerhouse. So for example, like the length or dimensions between two elements. And you can do also, for example, sectioning. So you can section, the view to visualize what is inside. So some basic navigation capabilities that actually, I would say, democratize the 3D. Everybody will be able to visualize the project and make, feedbacks on it. So now I will jump on CATIA to show you some more capabilities. So here I have, my project. So to manage the complexity of that project, so we used also a model-based system engineering. So using the FLP model. So R stands for requirements. So we can actually capture, all the requirements of the project. So the requirements, they can be put in as parameters, for example, that will drive the design, or that will be able also to run checks with those requirements to check if our design is complying with the different requirements. So then we can define actually the functional view of the project. So the functional view of the project. So that's the entry point for CATIA No Magic that we use also for MBSC at 3ds. And we can define also the missions, for example, for the project, like for safety, transport, power productions with nominal power, production shutdown, for example. You can define all the mission, the different services, like water supply, waste management, and so on. And we can also have access to the logical view, where you will see, for example, the different systems that you put, so, and subsystems. So in terms of, diagrams here. So those are intelligent diagrams. So it's not pure 2D. So you have objects here that you can, for example, edit. So here, I'm editing that object here. So we can see that, it's a storage tank. And this can be directly linked with the 3D. So we have a cross highlight between the 2D and the 3D. And then, so we have the physical. So the physical is actually, the design itself of the, the dam with the different elements. Where we can also work with different spaces. For example, we can define spaces for the, risk areas, for example. So if you have a fault, you can define a volume for this fault, for those risks. At the beginning, at the feasibility stage, you can pre-feasibility, you can define actually the volumes for the different infrastructure of the project. to perform different kind of analysis. And then, so if you look a little closer at the design, so here I created some slides, so like the slides that you have in PowerPoint, but we use that for design review. You can navigate in it and add some annotations if required. So I have my dam here, the powerhouse, which is here. We can see a closer look at the water inlets that are here, and then we have a tunnel that we will see in the next view that will go to the powerhouse here. So we can see then the powerhouse, in the context here. I have a more closer look at the powerhouse with the turbine enclosure. Then the section view. So here we can perform a section view. So I can navigate. So we have here, different systems. I will show that to you a little after. Here a cross section for the water inlet, for example. So we have the geology. So we can build, as I was mentioning, the dam in the context of the geology, defining, the risks that you will have with the geology, for example, to find the best appropriate area for the dam. And so with CATIA, I was mentioning the road design. So we have the capability to design the road with all the subgrade layers, for example, for the road, and we are getting accurate 3D quantities for the road. And finally, so the systems. So I was mentioning that before. So we have here the systems of the powerhouse, for example, with the HVAC, the ventilation. We have the electrical system that are represented, and then with the turbines, all the different pipes and so on. So it's to show you that we have really a global and a multidisciplinary approach. And just to end that, of course, we can manage a lot of different type of dams. So first one was a concrete dam, but here we have an earthen dam with different layers that are managed, in a cross section. I can maybe hide this just to show you that. So we can generate the dam with the different with the core inside and the different layers that will be used for the dam. So based on the dam axis and alignment. So that's it for my presentation. I wanted really to insist on the multidisciplinary approach that will actually allow you to bring all the different disciplines together in the same common data environment. Thank you everyone for listening, and have fun using CATIA.